at that time, she was the master student. So we're in the same class of Stanford Anderson, and also Stanford contributes a lot to Tongji, including our dean, Xiangning, and me. They invite us and gave us opportunity actually to learn, to study in MIT for a certain time. So it's a really impressive memory to me because Leslie had a really good performance when she was a student. And she is right now the assistant professor at Cornell Department of Architecture and directs the Rural Urban Building Innovation Lab and working with a non-standardized material and biomaterial. Her research and teaching explore the intersection of technology, novel material methods, and urbanization to experiments with the hybrid design and methods of making. By studying regional behaviors from the spatial transformation to the material source, her work contextualized design strategies with computational protocols and technologies like augmented reality and mixed reality to custom unique needs for the local community. So Leslie is also a co-founder of HANNAH, an experimental design practice that utilize innovative forms of construction to advance building practice. The works aim to mine the tension between the machine means and architecture ends. So the office is a recipient of the 2020 Architecture Legal Prize, named the Best New Practice of 2021 by Archidili, and named Next Progressive by Architect Magazine in 2018. So Locke also currently serves as Acadia's board of directors. Her work has been published internationally at Fabricate, RoboArch, Acadia, as well as the feature in Architectural Record and the New York Times, JAL, and the others. Her contribution were exhibited at the Total Museum of Contemporary Art in South Korea, 2022 International Architecture Biennale, Rotterdam, 2019 Bi-City Biennale of Urbanism and Architecture in Shenzhen, Art OMI, the Memory and the Canadian Center of Architecture. So Locke received her Master of Architecture at MIT. So today she would like to give a lecture named Lowering Material Narrative. I think we're sharing the similar vision because I think MIT actually influenced a lot to integrate what is high tech and low tech at the same time. So looking forward, we would like to give the screen to Leslie. Welcome.
Thank you. Thank you, Philip, for the kind invitation and the kind introduction. Indeed, it was 12, 13 years since we met at MIT, and it was a time just bustle with energy and excitement in terms of learning to design and research. And so Philip didn't mention, but he also took our entire class, the studio, to Shanghai. So that was, and to visit Tongji University. So that was a very, very fond memory. So thank you for having me here today. And I'm going to share screen. Okay, could you let me know if the screen is up?
Everything is fine.
Okay, great. So again, thank you, Philip, for the invitation to speak at DigitalFUTURES opening ceremony today. I guess in my talk today, I will be sharing the work from my design practice, HANNAH, that I co-founded with Sasha Zhivkovic, and work from the Rural Urban Building Innovation Lab that I direct at Cornell. And to begin, there's a glitch in the slide here, sorry. To begin, just elaborating on the presentation title a little bit more, there are certain concerns that drive our work: architectural, spatial, material, environmental, and technological. And so I would like to use the concept of unlogging to unpack some of these concerns and their conceptual entanglements in the presentation today. A log is both a part of a tree and an official record of an event during the voyage of a ship or aircraft, for example. And I think new material and design practices are needed to address climate change as one of the most pressing problems of our generation. And moving forward, architects, designers, and researchers need to develop new logbooks, log new design protocols, and fundamentally, in some way, unlog our past loggings in order to move towards a radically more sustainable and less wasteful building culture. So this environmental paradigm shift is accompanied by considerable design opportunities. We believe that the issues of making and forming are fundamental to how we operate as HANA. The various projects today would present are seeking to inform form through a variety of methods of production, from digital design, fabrication technologies, facilitating new material methods, to tectonic articulations, environmental practices, technological affordances, and architecturally expressive form of construction. So in the past few years, as Phyllis had mentioned, we have been very productive. We created open source contribution construction machines, which we argue inevitably affect how we think and design through making. So in our work, we aim to mine that tension between the machine means and architectural ends. And we built a small infrastructural framework for architectural exploration across scales, starting from the design of tools to prototypes and installation into a small building. In this process, just like the robot in this video, we have been trying to unlog our own architectural preconceptions and expectations. And I'll go over and start really quickly with just the tools of making. And so at HANA and our labs, we build our own tools, and these tools inform the designs on how we log our design. So when we started this work, we have to be inventive and build our own machinery to do the type of research that we want. And being able to do that allows us to unpack the manufacturing tool to influence the way we can build. And so while the machine is only a framework, our thesis is that with new tools come new architectural opportunities. So this is one of the first printers that we built, the Dataless. It is fully open source and costs only about $5,000 to make. And it's available on Open Source Factory at the RCL lab. And we also tried to build a robot. As it turns out, one can go to eBay and purchase a KUKA KR200 for $8,000. It is not free, but considerably cheaper than buying a new robotic arm. And so for us, I mean, similar to the printer, it requires a certain level of hacking. And for us, this robot enabled us to have another means of technological means to inform form and new material. So the first project I'll talk about is, and the first two will focus on the projects using the printer on 3D printing concrete. And in additive architectural elements, we discovered that the 3D printer, a machine which has long been characterized as characterless because it can presumably print anything, is in fact exactly the opposite. It has plenty of characters of what we like to call productive constraints. And most of these constraints are informed by concrete rheology and gravity, which we call the two frenemies of concrete 3D printing. Initially, our interest is in the following process. Like a three-dimensional drawing, the machine horizontally deposits one line after another. If the lines are shifted through corbelling, then it creates a spatial form. And so we find that in this very simple process is the complex language of concrete printing. In this project architecture element, our main design and research questions are, and actually is, what is the architecture of 3D printed concrete? And how can materiality and unique fabrication opportunities and constraints of the tools inform the design? So we started this project in 2015 and really kind of got the mixture in 2016. And so it happened quite many years ago. And so building the machine was the easy part, but with the aim of, finding out what is intrinsic to the additive manufacturing process. Like most people and most labs, we have to go through dozens of failures to understand the material's tolerance and its urge for imprecision. Also, when printing in concrete, the same rules apply as in the small desktop 3D printers, but gravity here takes on altogether different role in the process. So cantilevers will have to be carefully constructed, and new support material strategies have to be developed, and two paths have to be manipulated. So in this image, you see where we actually used a reusable gravel method to create temporary supports. From the design point of view, this project aims to review the 3D printer's highly idiosyncratic architectural tectonics and narratives. So we chose prototypical motifs like floor, column, door, window, wall, ceiling, and began to strategize how the simple layering of concrete and the act of corbelling can suggest new strategies for building. So in the first element, working with the constraints of gravity, the mushroom column plays with the cantilever over support material by printing upside down. And you see here with the horizontal striation, it results in a structure assembly that can seamlessly transition between the vertical and the horizontal. In the 3D printed structure, all common architectural motifs and building components must be rethought to fit the logic of layer construction. For example, a printer cannot print in mid-air. Therefore, the otherwise simple task of creating a rectilinear window opening in the wall becomes a de facto impossibility. So rather than drastically altering the process, stopping the machine to insert a beam, shortcomings become opportunities for design. And one logical consequence for the window is to cantilever incrementally and become a triangular corbelled arc. So suddenly, seemingly advanced technology relies on obsolete and archaic structural strategies such as corbelling. And that was a very exciting moment for us. Here you see the force column that is printed in section hints at the potential to deposit material where structurally necessary. And Smart Poché Wall explores the manipulation of concrete density to optimize for structural performance and to be architecturally expressive in the wall assembly. The ceiling element is an expressive play on ducts for ventilation, reflectors for lighting. It becomes a type of performative poché for building systems. The potential for excessive ornamentation is brought up in the door ornament. In the full-scale prototype, we were playing with the lamination of layers to create screen-like moments of transparency. So we see this manipulation of 3D printing rule sets as a tremendous opportunity where it requires the development of a new and different architectural language, which takes into account the limitations of the process as well as its performative advantages. There are certainly multiple narratives at play in this project, and we chose to present the work with a particularly speculative focus. We can also discuss the work in various other terms as well. From a technical point of view, there are multiple advantages to 3D printing, from constructed without the use of formwork and radical mass customization to material savings for smarter construction. However, there are severe shortcomings to working with concrete as well. The cementitious material itself has to change and become drastically more sustainable for 3D printing to become a viable future technology or current technology. So while our concrete projects exploit the design benefits of 3D printing, we as designers have a responsibility to dig deeper and constantly challenge the material we work with. And hopefully soon in the future, we aim to replace concrete with more sustainable alternatives. And to conclude this project, I want to say that undeniably there's a certain formal agenda at play here. And that agenda is derived from a highly deterministic bottom-up processes that is informed by the digital fabrication, and also top-down architectural decisions, which are perhaps harder to quantify and have something to do with our personal biases and design preferences. In other words, this is not a universal tectonic language. We also try to test out ideas across scales, and we're quite interested to see how certain intellectual framework change and transform while translating from one scale to another. So the idea of robotic mass customization inspired our Rolling Stones project, which was a winning entry for the Socrates Sculpture Park and Architectural League Architectural League's 2018 Folly competition. The design is deeply informed by program, in this case, public seating. And the brief call for a design that could be movable by visitors and staff, but solid enough that people are discouraged from removing it from the park. So with concrete gravity working in our favor this time around, we got the second part covered from the get-go because they're hard to steal. Leveraging movements architecturally, the folly itself and the folly themselves, the chairs, the playful design encourages creative interaction and allows park visitors to discover a variety of seating. Responding to the scale within the public park landscape, the Rolling Stones can form a long continuous bench object or aggregate into smaller benches or disperse entirely to form different size seating groups or solitary compositions. And 3D printing with concrete enables the creation of 25 affordable and self-similar, but ultimately entirely individual seats. And so no longer bound to the relentless paradigm of standardization, the 3D printing here opens the possibility for design freedom, customization. And as you can see in this photo, concrete is indeed hard to steal or roll, but with two people, it's actually quite okay. The material used in the 3D printing process is Portland cement-based mortar, which is reinforced with nylon fibers, resulting in a strong concrete assembly. In addition, each seat is supported by 3 steel rebar profiles embedded within a double layer of concrete, as you see in the photo. And to enable the creation of some of their cantilever forms, the seat's interior is supported with a bed of gravel during printing. A layer of gravel remains imprinted on each chair's interior surface, giving it a geologic character, also an honest reading of the fabrication process. And so here is a short video clip showing the making of the Rolling Stones from some of the initial prototype that you see here to the material testing and fabrication process. And so the idea of the bench, the seating could be contextualized and used in different ways at the park. And so so the printing is, again, very simple, where it's, using the sort of singular extrusion layer by layer. And you can see that the printing itself is not an autonomous process, but rather it's like an interplay between the human and the machine. And for reinforcements, we've tested different types of reinforcements, from steel rebar to hemp fiber to steel fiber to fiberglass. And in the end, we end up with going for steel rebar. And here you can see the printer printing the double layer with the rebar profile embedded. And then so there are 3 rebars in each seat to prevent it from breaking, as it's a public seating. And so there's, again, us dancing and working with the machine together. And here is the printed form. So it takes about a day to print 8 seats. And here, of course, it does depend on the project, how much we print per day. And here's some material testing, and that was installed at the Socrates Park in 2018. Since then, it's been moved to a couple other places. And the next project is Hollow Wall. So the Hollow Wall is a project by Rural Urban Building Innovation Lab. And it looks at the explorations of using non-standard and non-uniform material with augmented reality and mixed realities. So this project focuses on upcycling non-standardized wood elements to create customized structural wood system. And so this with this project, then we shift to another material exploration in this case, which is wood waste. The project design narrative is consisted of 3 main aspects, and the first is using salvage material. Wood accounts around 10% of all material deposited in landfills annually. And the project used these reclaimed wood actually from wood boards from a collapsed barn in our neighborhood, in our region, for a more sustainable approach in building practices. And here you see then the reclaimed wood were processed with initial cleaning and marked. The project also referenced traditional windbreak shelter and agricultural landscape. The Hollow Wall is a repository of cultural traces for the emblematic and utilitarian windbreak walls that protect livestock and buildings. And the design explores the coupling of AR with these non-uniformly sized wood boards to develop a digitally informed and customized hollow core CLT wall assembly. So you see the process here kind of outlines the wood source, and they were scanned and actually processed then with AR, MR tools and assembled, fabricated in that way as well. So first is a material exploration in CLT. The installation introduces a customized hollow void core that is enabled by computational technology to reduce material use. And so the initial design started with the wind analysis, giving its function as a windbreaking wall, looking at the local wind rows, direction all season, and then doing CFD analysis of the walls with the wall's new geometric configuration to see how it responds to the wind from the predominant directions. And by selectively reducing core timber to optimize the void volume, the installation saves construction materials and leveraged the cavity as a design parameter. And the structure adopts multiple design parameters to customize these panels, such as structural performance, wind deflection, and view interaction to inform its thickness and porosity. And here you see the sort of structure analysis series that it went through, from the solid to a generic void to a customized void, and a varied number of layers of thickness and thinness. And at the end, the project has a void volume of about 30% of material was reduced in its usage. And so here's a close-up of the installation, showing some of the more regularly spaced and also irregularly spaced conditions. And this is the installation on site. And to speak a bit more about the AR and MR informed processes, there are mainly 3 steps. One is processing the material, which entails the marking and cutting. And second is the assembly and fabrication, which entails the dry laminating and gluing and on-site installation. So first, an MR guided material process is used to provide a user-friendly working interface to upcycle locally sourced wood waste. And this visual guidance projected through, we use the HoloLens, allows users to intuitively engage with the material's irregularity. And so you can see in the drawings on the left, the boards are sorted according to their thickness, and the maximum usable rectangular area are computationally calculated and sorted. So that allows us to maximize the usable area of the wood board that we source. And this drawing shows the semi-automated wood piece toweling process. And it starts with an automated process, and then manually by selecting pieces that can be also reused for other parts of the boards. And in the MI guiding process, after being digitally recalibrated to maximize the usable area, you can see here the visual development allows us to understand which part to use, which part to cut, and which part to save. So every graphic elements is different, whether they're opaque, solid, and whatnot. In the mixed reality guided laminating process, users can first dry laminate each layer to check for geometric and dimensional accuracy. And also for initial dry laminating for more complex pieces. And subsequently, each component is laminated through the holographic gluing position, as you can see in the video, because as the spacing change, the gluing position also changes. And lastly, the AR side of the function help us actually situate the position, orient the installation on site, as well as immediately we can just go right ahead and place where the foundation anchors, the ground anchors would be. And so this project, similar to many contemporary digital projects and AR and MR projects and processes, that we didn't use any drawings in this case. And here is another picture of the installation. So moving to the next part, which I would like to just highlight a little bit on talking about the material that we use for the next two projects, which it's on the emerald ash bar infested wood. We call it a morbidly sustainable biomaterial. The invasive EAB threatens to eradicate most of the 8.7 billion ash trees in North America and has drastically transformed the entire forest ecosystem in the process. And as of October 2018, it is found in 35 states in the US and several Canadian provinces. And this is something that we encounter actually in our backyard. So that's how we actually came to learn about this, epidemic. So what you see here, this beautiful bug, the emerald ash borer, is actually much tinier in real life. They look huge on the screen. It's a small beetle whose larvae hatched underneath the tree barks and cut off vital layers that transport nutrients within its trunk. And as a reference, almost every 10th tree in New York State is an ash tree. So while we as designers cannot help the dying trees, we believe that the infested trees form an enormous and untapped material resource for sustainable wood construction. And what you see here is an image of the Arnott Teaching and Research Forest at Cornell, where all our wood comes from. The EAB arrived here in 2018 in our backyard, and is the source for all of our ashwood projects, including the next two projects that I will talk about. So first is Unlog. Conceptually, Unlog investigates how far a singular log can be stretched, both literally as an assembly and also figuratively as a resource. The research focuses on the development of a lightweight and easily deployable timber framing method, utilizing robotic curving techniques to transform the EAB-infested trees into material efficient and valuable resource. Unlog uses logs that can unfold from a line, a column, to a surface, loosely referencing and reinterpreting the American tradition of wood framing. And what you see here in this drawing is the log utilization comparison with framing using dimensional lumber compared to the stretch robotically curved logs. And we ask ourselves, can we make this method of construction more efficient with framing? Can we use decaying hardwood to rethink framing techniques? And the full log curving methods was initially developed by Savannah Chase and Hawk in the Timber Villa Option Studio at Cornell in 2017. So the diagram here illustrates the geometric relationship between the uncut margin and of the component and its transformation of spacing. So the image on the left is an initial test that we cut at a workshop at UVA. So this method enables the simple creation of a bending active structural component with a material integrated hinge, as you can see in these drawings. And it also has very interesting characteristics because depending on the distance you spread, the top and bottom edge would also change in height. And so in terms of cutting the end to anticipate certain deformation also could be an interesting parameters to consider. So for this project, a comprehensive method for full log curving was developed. In woodworking, curving is reliant on a relief cut technique that is used to induce flexibility into a material, and is often applied to sheet material to generate surface curvature. However, curving here is used in altogether different capacity, and the project employs method to robotically curve a log along its length using the alternating cut pattern as you see in this GIF. And so that the log can begin to unravel into from a volumetric round wood into an operable leaf spring component. And this constitutes the overall structural logic of the structure system. The zigzagging logs can also be used to create brace structural assemblies and propose a new transportable and zero waste construction methods. So a large variety of natural log geometries, whether straight or curved, can similarly be sliced and curved using this framing method. As you can see here, we have the regular straight logs on the left, curve, and even maybe begin to optimize the thickness of the cut of the curving geometry to allow for an optimization of structural performance. For the unlog installation, we use the regular curving geometry. So a preliminary test of the structural component you can see in these diagrams here. So for the simulation, it was assumed that each board would have a have a pin support, and only gravity loads were applied to the model. And the simulation found that the bending active A-frame to have a significant structural viability with only a few millimeters of displacement. And this method was reapplied to the whole installation. And so that was the sort of material and structural investigation just now. And then to consider the site, we were exploring and the three trees. There are three huge, beautiful trees on site. So we decided that the spatial A-frame should strategically frame the three large trees on the installation site to engage with the context. And so this is the resulting spatial configuration where each log is oriented and framed a view centrally towards one of the trees. And it's site plan. And as you can see, the structure is made of 3 A-frames with 2 curved segments connecting them into one linear structure. The project used a total of 6 logs. Here are photos showing the installation on site. The logs, the trees. And so to then kind of present the overall workflow, it's actually fairly straightforward. We sourced our log from on Cornell grounds with mature ash trees. We use mostly strict elements that are compatible with current logging protocols. And in the process, it involves AR and MR to facilitate certain part of the assembly processes. We also CNC milled as custom slip washers, and the woods are robotically curved using our facilities at Cornell. So in the first steps, the logs were cut in half along the longitudinal axes with the robotic arm. And the 6-axis and with the bandsaw end effector, after each profile were cut, the log is rotated 90 degrees and mounted on the robotic cell and start to make alternating cuts. Also using twin bill, the AR interface was used to instruct the assembly team on the location of the timber members and therefore their hosted threaded rods. And through this prototype, on the right, you see that we built a full-scale prototype, and it actually helps us to understand the misalignment between the digital and physical models, because the physical mock-up reflects the actual bending property of the curved log much better. And so we were able to then use the physical mock-up to update our digital studies accordingly. And so AR was used to inform and modify prototypes and therefore enhance the digital models accordingly. And so this is how the installation arrived on site. 6 logs. We have an extra log for the gallery exhibition. And with all its hardware, ground anchors, the entire structure weighed less than 2,000 pounds. And here's a photo showing near the end of the assembly, we were putting together the sheathing. Here is an image that shows the assembly detail, illustrating the assembly sequence and the custom slip-on washers that we developed specifically for this project. And here's another view showing the relationship between the threaded rod, the washer connection, and then the robotically curved logs. And on site, it creates this curvature that then creates a space that looks towards the street and a space towards the building. Materially, the project also, because of the process, one can start to see it has both the sort of clean, precision, precise edges with robotic fabrication tools, but it also retains the raw and natural edges and qualities of the bark of the logs. And the image on the left shows these robotically sliced ash boards. They're about 2 millimeters thin that we use to create the sheathing for. And here's a corner detail of the radial connection, radially curved connection. So the installation has now found, after the installation, has found a new home at the nearby art gallery and community garden. So the video shows installation at its original site. And this project, from unlog to log and back, because it was disassemble and reassemble again, the structure can be easily moved and reinstalled, thus presenting an easily transportable, deployable, circular, and minimal waste construction methods. And so the last project that I want to share with you today is perhaps accumulation of the different separate research agendas that you've seen in this lecture so far. The Action Cabin is a project that started in the summer of 2017 and was finished in the summer of 2019. And it is informed by 2 material narratives. It is a small building made of 3D printed concrete and a robotically fabricated timber envelope. In the first material system, the cabin explored, similar to the additive architecture elements, how the horizontal layering of concrete and the act of corbelling can suggest strategies for building. And so the concrete structure is printed in components that function as sacrificial zero waste formwork for the main structure. They are printed in small section and transported to site and manually assembled, as the site is in a quite remote condition. So here you see some of the printed pieces and the custom rebar cages for some of the legs. Now and then here's a top view of the site before anything else was there and the initial components being on site. So we develop a hybrid construction system where 3D printing, formwork, and cast and concrete with custom rebar is used to provide the main structure. Each leg is filled with foam in the void, and concrete is poured in between. And here you see it's the base and the chimney is going up. And the slabs are organized in a 9-square grid, reflecting the interlocking pattern of the legs beneath. In this hybrid building process, tectonic expression is generated by the fabrication method and materiality. For example, the G code here and the print path becomes visible as the ornamental pattern of the 3D printed floor slabs. And corbelling is achieved through sectional transformation to become an expressive and functional motif, allowing the horizontal layers to seamlessly transition from the leg to the slab and into the chimney above. The resulting concrete structure lifts off the ground and is characterized by 3 programmatic areas: a table, a storage seat element, and a 7-meter tall working fireplace. And so this was designed and constructed in the span of one summer in 2017. And so the second part of the cabin is actually really informed by the emerald ash borer epidemic. And we were thinking how we could use this material. So due to their geometries, many of these infested ash trees cannot be processed by regular sawmills, and they are regarded as unsuitable for construction. So challenging preconceived notions about material standards and woods, the cabin utilizes these infested trees for its envelope, which unfortunately are widely considered as waste or mostly used as firewood, releasing carbon back into the atmosphere. We develop a process that involves 3D scanning with our custom robotic platform and to transform irregularly shaped wood into an abundantly available, affordable, and morbidly sustainable building material for the Anthropocene. So with this method, we can slice irregular tree logs into naturally curved boards and strategically assemble the boards to form different surface conditions. Ironically, in order to advance environmental resiliency through architecture, we use resources that themselves were not resilient enough. So by adjusting the thickness of each cut, the robotically carved boards can be assembled into single curvature or double curvature surfaces. The trees were selected based on log diameters and curvature features. And the selection that you see here for the cabin presents a normal cross-section of available geometries that fall within regular parameters of the tree growth. And so to process and design with the logs, geometric form finding and assembly protocols from form to log and log to form were developed, which allow us to toggle between the original design, the material, and how that back into refining the overall structure and form. And here in this image, it shows how the logs can be sliced with different thicknesses. The slice boards are then arrayed into an interlocking SIP facade panels. It follows the logic of a structural insulated panel, essentially an inner and outer layer of ash boards and spray foam section. And encountering when we do build a building, despite this small scale, certain disciplinary problems such as question of joinery, material connections, proportion, and performance begin to re-infuse our discussion. And so as you can see here, the facade is then a fully ventilated detail to manage shrinkage and does not require an additional ring screen. The end result of this constant negotiation is an unfamiliar hybrid between digital and the anachronistic processes of construction. Returning to the point, oops, can someone mute themselves? I can hear ya. And so architecturally, Ashen Cabin walks the line between familiar and unfamiliar, between the technologically advanced and also formally elemental. The undulating wood surface is strategically deployed to highlight moments of architectural importance, such as windows, entrances, roofs, drain scuppers, or canopies. And on the inside, we use predominantly straight ash tree sections to create a contrast between the exterior and the interior. And also the height of the panel layering correspond with the openings that we create, whether if it's looking into the landscape or looking into the building. So no longer bound to the paradigm of timber standardization, such as 2x4, this project revisits woodcraft and design based on organic found and living materials. While transformed, the natural tree remains legible in the design. And the cabin combines a variety of fabrication methods, material applications, geometries, and types of constructions. And here's an interior view showing how conventional framing of the roof with 3D printing and robotic wood all come together. Both rigorously and playfully, the research in robotic timber fabrication and concrete 3D printing embraces a complex set of layered design narratives, leveraging technological advancement to reduce material waste and to encourage the comprehensive usage of resources in architectural projects. By fully unpacking the manufacturing process from the ground up, thereby presents an exciting opportunity for architects and designers to reclaim authorship over new processes of construction, which influence we can build, how we can build, or perhaps even how we ought to build in the future. And so again, multiple narratives have, whether they're ecological, technological, or architectural, are unfolded in the various projects. So with this image from the Unlog project, going from the unlog back to the log, I would like to end this presentation. Thank you.
Great, fantastic. I think it's a remarkable lecture. I'm very happy to see in the past 10 years, actually, Leslie make a huge progress and really special authorship and contribution to society, not only design the building, but most important, the cross and the toolbox and the special framework to set up. Actually, if we have certain opportunity, we would like to exchange our last 10 years because we're doing very similar achievements, but approaches are different because the social background and the project's different. But I think the thinking methodology is very similar. So that I'm very appreciative to see what's happening in Cornell because we know Jenny Sabin well and also you, close friend. So I think looking forward to find some special opportunity to make further communication with you. So we have Rosanna, who is the chair of Architect Department in Tongji. So I would like to invite Rosanna. Are you here? Would you like to address your comments and the question to Leslie? She is actually in New York City, so not so far away from you. So I think the research method is quite interesting because you firstly design some robotic and also the digital fabrication tools. And also you implement like G-code, this kind of software, hardware integration platform. That is something like also the design production of yourself firstly, and then goes to certain project. So I think that's the very special scenarios or the phenomenon practice in the past few years, because like some university, like University of Princeton, I remember they also have a team make research on the log, and also some 1 or 2 teams from Europe. Also, we invite them to make speech on the platform of DigitalFUTURES. They make research on the log, but I think the approaches are different because of the toolbox you set up are totally different. So could you analyze and tell us some your fundamental thinking about the future authorship of architects? How would you like to set up the framework of your practice? And do you think that will totally change the future practice and future education based on such kind of new authorship you put forward?
Well, thank you, Philip, for the question and the comments. Yeah, I think with the tools is a really important part of our exploration, and in a way, it's a very open-ended process, and it does. I mean, I think the conception doesn't come out of nowhere. Meaning that when we built the printer, we were already interested in exploring 3D printing concrete at full scale. But we didn't have the machine for it. So then we have to build it to do it. And then that kind of facilitates further investigation, and design opportunities began to emerge. So when we built the printer, we didn't know we would go build a 3D printed cabin, for example. And similarly with the robotic tools, we were interested in, of course, going beyond, the 3 axes. And so we actually started using the robotic arm with 3D printing. And we discovered this ecological crisis of the ash trees, and that prompted us to do something. And so now that the tools is in our control, it gave us the freedom and liberty to then explore and customize it according to new material narratives, new ecological narratives that emerge in the process of design. So I think that relationship is a reciprocal relationship. It's back and forth, and that's what's so exciting about it. And as you saw with the unlog and the cabin, there are different ways that can be then developed and used to explore the usage of these waste wood. I do think moving forward, to scale up, to engage the larger construction industry, it is important and helpful to understand, for us ourselves to understand what are the advantages, but also shortcomings of these techniques, and perhaps hybridize them with conventional techniques to engage building industry in the larger scale. Because if we continue with just focus on these idiosyncratic methods and processes, there are challenges to scale up because you're unable to engage a larger audience and community. So currently we're working on a full-scale 3D printed house. And so that involves actually working with industry partner, working with structural engineer, getting it permitted and so on and so forth. So it's learning to also being able to hybridize and how to adopt and adapt conventional methods with these new emerging technologies.
Yes, we can see some very interesting, like where in Stanford Anderson's courses, he actually introduced this kind of high tech and low tech. He makes some comparison about GSD and MIT when they have different things at the very beginning of modernism time. So we can see some roughness that's coming from the localization or local materials, and you find a lot of approaches that's actually not very high tech, like the log select, like the concrete print. I think it's very localized approaches. But at the same time, you have some very advanced technology like VR and the robotics hardwares that's actually it's advanced technology. So I think we make a lot of discussion in the past few days on our PhD courses. Like Lim Yang, he gave us a special talk, lecture. He is talking about after 2020, the trend is moving like is going on like all the planet goes to localized because we find the carbon footprint, everything, you should find something very locally from nearby, including the materials, like you find some logs just in the backyard or in the mountain which surround the campus. At the same time, we have some global technology which actually totally change the methodology and thinking methodology and design process, which is like the virtual reality and VR, like robotic technology. I think that's two kinds of trend which is mixing or hybrid together to give us a new opportunity to create the value or I think that's something maybe for the future in the discipline. So I think especially your last project is quite impressive. I remember I first see it from Eric Hollow's Facebook. I think it's very early before you publish it. Maybe he visit your production site, and I see it's all what I say, wow, it's a super interesting project because in the modernism time is so difficult for architect to engage into the process because it's like the prefabrication in your small house is everything should be modeling and should be like positioned accurately in the location. And also if you think about the insulation, waterproof, such kind of things. But at the same time, we can see the roughness of your printing machine. We can say our concrete printing machine is most accurate compared to yours. But I think this kind of roughness produce certain kind of value. That's super interesting to me and on the facade. So do you think your future future practice, would you like to buy more robotics and to improve your technology to more advanced direction, or maybe the other option will be probably the same to what they're doing, actually focus on this kind of roughness, which produced by the advanced technology, maybe it's based on the, it's not very advanced, but which produce the value of the, it's like the material touch. If we can touch it and to feeling it, that produce certain kind of quality. Maybe it's a kind of intelligence, but which is totally different to the advanced technology or intelligence we produce from the research or from the studio workshops. So how would you like to position your future practice? What's the next for your research and practice?
Yeah, I think that's a very insightful way to contextualize the work. We're interested in both, in the sense that the tools is a machine means. It's a machine means to an architectural end. So the machine and the technology, the tools itself, is not the end goal. I think ultimately as designer, we're interested in architecture, the design. And so it's the means is important, but the end is also very important. And so I think like, you said with the printer, it was like the most basic that we can get to get it to working, and to explore what we want to explore. So definitely we are we are working on, refining the technology side, readapting as we go. Also engaging with larger industry partners where their tools might already be at a certain level, where we want to use our energy on then focusing, exploring new material methods and scaling that up and testing it. So I think we're interested in technology because it's so important, because it informs the ends, but we're not interested in technology alone in itself. So I would say hopefully we'll be able to continue to expand in both respects relationally. Yeah.
Thank you. Thank you so much, because the schedule is very intense for us. I would like to say thanks a lot to Leslie and for your contribution to the society, and it's great, remarkable lecture you gave us. So actually, we put all the lecture to Bilibili YouTube. So on YouTube, we have around 300 lectures, and the viewers more than 400,000. So that's a big number. So hopefully, in China, we use Bilibili. That's another platform like the same YouTube in China. So I think both platforms will introduce you to the audience. I think you are the future, and we're looking forward to see what's happening next to you. So thank you for coming.
Thank you, Philip, and I look forward to exchanging later on, getting back in touch. Bye-bye.
Thank you so much. And we have